Here is our objective. I can find the rate of change and slope from tables and graphs. And those are, again, the same standards that we worked with yesterday on rate of change and slope. Sorry. Here's our key vocabulary that we need to make sure we understand. You should already have this in notes from the notes you took yesterday, but I just want to quickly go over it. So if you have it in your notes from yesterday, you don't need to copy it in. We've got rate of change. Rate of change shows the relationship between two quantities where one is dependent on the other. So this is what it looks like. Rate of change equals change in the dependent variable over change in the dependent variable. So we're talking about divided by, right? This is a fraction, change in the dependent variable divided by the change in the independent variable. Rate of change, independent variable. Okay, so what is a dependent variable? Our dependent variable is that y variable, and that is the effect variable. We call it the effect variable. It is influenced by the cause. It's dependent on the cause. So the cause, which we're going to find to be as our x variable, is going to cause this y to change. So the y is determined by whatever's happening to the x. So our independent variable, that's that x. And that's the cause variable that influences, okay? So the x influences the y. It causes the y to change. So our independent variable here influences and makes changes into the dependent variable, which is our y. Independent is our x, and dependent is our y. So the ratio of a vertical change to a horizontal change, the rise over run, or our steepness. So we think about this like on a road. You see steep road signs where you see a truck on a triangle going up a steep hill or down a steep hill on a triangle. Steepness, that's slope. Okay. So what that looks like here is our slope equals our vertical change over our horizontal change, or we call that our rise over run. So you can count how many you rise from one perfect point and how many you run to the next perfect point. So here we are running 1, 2, 3, and we are rising 1, 2, 3. So our slope for this line would be 3 over 3, or reduced down to be 1 over 1, which would be 1. Okay, so in this case, we picked 2 perfect points, but we didn't pick the 2 that are closest to each other, so we had to simplify it. It's fine. You can pick any 2 perfect points. They don't have to be the 2 closest, but if they're not the 2 closest, then you'll have to simplify. All right, so finding the rate of change using a table. So here we have our rate of change, and we have this table of time and distance. When we are looking for our dependent and independent variable, we're looking for the cause and the effect, right? The time is going to be the cause. This causes the distance to change. So as we increase our time, our distance is going to change, okay? It's not the other way around. You don't increase your distance to increase your time, okay? As you have more time to run, or to, in this case for the turtle, to walk, right? As you spend more time doing that, your distance is going to increase. You're getting more distance, okay? So here, distance over time. I want to point out that when you are comparing time to something else, time is almost always going to be your denominator. It's going to be your independent variable. Time is always going to be that cause, okay? It's going to cause the other to change almost every single time. So if you see time, you can generally just put that in the denominator as your independent variable. So here we're going to compare what's happening from when we go from 1 minute to 2 minutes, okay? So here we've got 12 minus 6. Our distance, 12 minus 6, okay? This is our y2, okay? y1, so 12 minus 6. This is our x2, our x1, so 1, 2 minus 1. And when we do that, we get 6 over 1. Here, then, we're going to go down to the next set, and we're going to take 15 minus 12, and then 3 minus 2. And then we have this last one, 21 minus 15, and 4 minus 3. And we're looking here now, we're looking at each of these rates of change, and we're trying to decide, is it constant? Is the rate of change constant? Is it the same all the way through the table, right? So here, our rate of change is 6 over 1 or 6. Rate of change here is 3 over 1 or 3. And the rate of change here is 6 over 1 or 6. You'll see that these two are the same, but this one here is not the same. So the rate of change is not constant. It's not the same. So no, the rate of change in this table is not constant. So we can't give it a numerical answer. We can't say the rate of change is 6 because it could be 6, it could be 3, all right? It's not going to be the same every time necessarily. So that example, rate of change is not constant. So let's look at another example. Here we've got an airplane descent, and we've got our table with our time and our elevation that we're comparing to each other, right? So again, time is going to be that independent variable. We always put that in as our independent variable, and 99.99999% of the time, that time will be your independent variable. So elevation would be our dependent variable. The time is going to cause the elevation to change. So this is our table, this is our table put into our y2 minus y1, right? To find out our change here. So we've got this 29,000 minus 30,000 over 2 minus 1. And then we've got the 27,500 minus 29,000 over the 5 minus 2. And then we've got the 24,000 over 27,500. I'm sorry, 24,000 minus 27,500 over the 12 minus 5. All right, so we're just comparing what's going on as we change levels of time. So for the first one here, we get negative 1,000 over 2. The second one, we get negative 1,500 over 3. And then the last one, we get negative 3,500 over 7. When we simplify or reduce these fractions down, we end up with negative 500, negative 500, and negative 500. They are all the same. So yes, it is constant. The table is constant. Our rate of change is constant. It's the same. So what is the rate of change? We give it the numerical value of that negative 500. We're going to use our independent and dependent variables in our answer. What does the rate of change mean? In this case, the airplane descent, it means that the plane is descending 500 feet per minute. It's a negative 500, so it's going down. Descending means going down, okay? Other times when you have a negative, it might be decreasing might be the word you're using, right? Your rate of change, when it's negative, you're decreasing, you're subtracting, you're descending. One of those type of words, all right? Rate of change here, we're comparing hot dogs to buns. So when you think about when you go to make hot dogs, right, you pick out how many hot dogs you're going to make. And then you make sure you have enough buns to fill those hot dogs, right, to put those hot dogs into. So generally, you don't go to the store and buy a bunch of buns and then say, oh, I need hot dogs to put in these buns, and I need to get the right amount of hot dogs to go in the right amount of buns that I have. No, generally what you do is you buy your hot dogs, you decide how many hot dogs you're going to make, right? And you then make sure that you have enough buns for each of those hot dogs. Right? So the hot dogs are the cause to the buns, which are the effect. The hot dogs, the number of hot dogs, cause us to buy the right number of buns. So here we are, buns dependent and hot dogs are independent. So over here, we've taken our information out of our table and we're comparing when we go from 2 hot dogs to 1 hot dog, we are going from 2 buns to 1 bun. You'll notice that this is a 1-to-1 relationship, right? This is a 1-to-1 ratio because generally when you get hot dogs, you want a bun for each hot dog, right? You want to put 1 hot dog in each bun. You don't usually put 2 hot dogs in 1 bun, right? And you don't usually take 1 hot dog and put it in 2 buns. It's a 1-to-1 relationship normally. So you're going to see that each one of these, right, is going to give us reduced down to be 1/1, which would simplify to be 1. So they are going to be a constant rate of change, okay? So yes, it is constant. The table is constant here. And what is the constant rate of change? It is 1. 1-to-1 right there. Every time we're going to have 1. So what does the rate of change mean? It means that there is 1 bun per hot dog. So for every 1 bun, there's 1 hot dog. Okay? 1 bun per hot dog. Each hot dog gets 1 bun. All right, so now we're going to move on to. Okay, so slope is our steepness. These are a couple picture examples of some pretty steep hills here, right? Slope formula. Slope formula is this nice little italicized M that represents slope. When you see that M that's italicized like that, we're saying slope. Slope equals, or M equals, y2 minus y1 over x2 minus x1. So we've got slope equals our italicized M. So slope equals M, which is also referred to as rise over run. And our formula there is y2 minus y1 over x2 minus x1. Rate of change. So we're looking at versing the slope versus the rate of change. So we're looking for what's different here, right? Rate of change looks like this. It's the change in the dependent variable over the change in the independent variable. So our rate of change versus slope, again, here, we've got our slope formula here, right? y2 minus y1 over x2 minus x1, which is our rise over run. That's our slope. Rate of change is that change in dependent variable over the change in independent variable, which what we do to get that is we take our y2 minus our y1 over our x2 minus our x1. So you say now, well, so what is the difference? It's the same, right? We've got y2 minus y1 over x2 minus x1. Here we've got y2 minus y1 over x2 minus y1. And in some aspects, yes, it's the same. The formula is really the same to find them out. But we're going to find out what the difference is here. As we look back at these other examples that we went through on finding out if they were a constant rate of change or not, right? We had the table on the turtle walking and we had the table on the airplane descent. If you look over here at the turtle walking, you'll see that this is not a straight line, okay? And you'll see on the airplane descent, we do have a straight line, okay? So what does that mean? Well, when we look at the turtle walking, we had a rate of change of 6, and we had a rate of change of 3, and we had a rate of change of 6 again. So it was not a constant rate of change. We had 6, 3, and 6, all right? They were not all the same. So we could not give a single rate of change value, okay? So that was not constant. And these boxes were supposed to come off when I clicked, but I didn't do that right. So this should say not constant, not constant. Over here on the airplane descent, you'll see that we do have a constant rate of change. The rate of change is negative 500 for each of them. So this would say constant. It could give a single rate of change, which was that negative 500. It descended 500, all right? So the difference here with rate of change and slope, this turtle walking graph, this is a representation of a rate of change. It can vary. It doesn't have to be the same. It doesn't have to be constant, okay? It doesn't necessarily form a straight line. This is an example of slope. This is a straight line. So the rate of change is constant. So when we're talking about slope, it is a rate of change, but it is a constant rate of change. It has to be constant. Again, the rate of change, it can be constant, so it can form a straight line, but it doesn't have to, okay? Slope, it has to form a straight line. So the difference between the rate of change and slope is that slope is used to describe a straight line. Okay, slope is going to form a straight line, no curves, no bends in it, all right? While rate of change can be used to describe lines that are not always perfectly straight, okay? They can be, but they might not be. So back to slope. Here we're looking at how steep is the steepest roller coaster. So we've got 4 examples of roller coasters here, and we're looking at how steep they are, right? So this is a pretty steep roller coaster right here, right? Okay. So imagine a roller coaster moving from left to right. So if we're going on looking at this picture and we're moving from left to right on this picture, we see that over here, right now the roller coaster, the riders, they are in a negative slope. They're going down the hill, right? And then it's going to kind of even out here, flatten out, and then they're going to start their ascent. They're going to go back up. And then this is going to be a positive slope here, right? Going down is that negative slope, descending, and going up here is that positive slope. They're ascending.
Dude, remember always what he said during his ski trip. Up the hill or up the slope, he said, puff, puff, positive. On his downhill run, he said, nice, negative. On the long, flat part of the course, he said, this is zero fun. And finally, when he went over the vertical cliff and went straight down, he yelled the worst curse word of math and algebra, undefined. The uphill is a slope with a positive number. The downhill is a slope with a negative number. The flat part is a slope of 0. And the straight up and down or vertical part is undefined. This has been the adventure of Slope Dude.
Okay. So here's just another graphic to help you remember that. The roller coaster, right? The roller coaster is going uphill. That is a positive slope. Puff, puff, positive, right? Going up the hill. Another way to think about that is if you were to take a pencil, right, or pen or whatever, and move it across your graph. As you're moving it across your graph, if that line is moving up the graph as you're moving, right, then it is a positive slope. If it's moving down, the line is moving down that pencil as you're moving it across the graph, it is a negative slope. You can do the same thing with your finger, marker, whatever. So here we have the roller coaster going down the hill, giving us a negative slope. Nice negative. Here we have the roller coaster going horizontal, right? Flat across, and that's zero fun. Zero slope. Zero fun. Just no hills, no slope. Zero slope. The vertical, this is the white knuckle ride, right? You're going straight down on that coaster, vertical. And that is undefined. Undefined. All right. Here we go with using a graph. So how do you calculate the slope of a graph? There are 3 steps. First, you pick 2 points on the line, and you need to pick 2 perfect points. I'm going to talk about that on the next slide here. You're going to calculate the rise over the run, and you're going to determine the sign. So here we've got a graph, and we've got a whole bunch of points picked out. We're going to start with 2 points on the grid line intersections. So you're looking for perfect points. That means that you're looking for the points like this one, where they are at an intersection on the graph. It doesn't have to be where your X and your Y axis intersect at the 0, the origin. It just has to be where you have an X and a Y intersecting, right? It doesn't have to be your origin. So here, this one here, this is a perfect point because you can see that it is at the intersection of an X and a Y. It's right there at a plus. It makes a plus. A plus is going through this perfect point. This one here is not okay. It's not a perfect point, so we don't want to use that because you can see this X is going through here. I'm sorry, the Y is going through here, but there's no X intersecting it. It is not forming a plus. It's not at the intersection of a plus, right? So that's not okay. We don't want to use that. Here's one that's okay. We would have a plus right there. Here, not okay, no plus. Here, again, we're okay. We've got a plus. Again, not okay. There's no plus. There's no intersection at all. No lines going through it. Here, we're okay. Again, we would have this plus here. So you want to pick 2 perfect points. You can pick any 2 perfect points. I personally like to try to pick the 2 perfect points that are closest. So I pick one, and then I pick the very next perfect point. If you pick 2 perfect points that are closest to each other, then you don't have to simplify or reduce later. But if you don't always see those 2 perfect points. If I pick this one and this one, I would just simply have to simplify and reduce when I got to that point. So here, how do you calculate the slope of a line? So we take our vertical change, that's our up and down. Either way, it can be up or it can be down. That's our vertical change, okay? Think about that in basketball. You talk about vertical, right? What is vertical? You know, and that vertical is how high they can go up, right? How high they jump up. So that's the up or down. Then you've got your horizontal change, which is your run. That's what you're running, okay? Rise over run. So our slope, M, equals our rise over run, or the vertical change over the horizontal change. Same thing, right? And we just count them. On a graph, we just look and we count it. So from this point to this point, we would rise 1, 2, and we would run 1. So our slope for this line would be 2 over 1, or 2. Okay, so what sign is it, right? You look to see if the slope is increasing. If it's increasing, so it's the roller coaster is going up the hill, the skier is going up the hill, puff, puff, positive. It's increasing. It's positive. If it's descending or decreasing, right, it's going down the hill, it's negative. Nice negative. All right, so to find the slope again, our fact, points on the same line always share the same slope. So you could see more than 2 points right here, right, to use. You can use any 2 points you see to calculate slope. So I could pick this point and I could pick this point, okay? In this case, I'm going to go ahead and pick these 2 points that are the 2 perfect points closest to each other. I could have picked this one and this one, right? I could pick any 2 perfect points. But if you pick 2 that are right next to each other, you're not going to have to simplify or reduce later. So we've got these 2 points, and I'm looking for my rise over run. So I'm looking from this point to this point. How many boxes am I going up or down? Well, I'm not going up or down, right? So it would be 0. 0 fun. My rise is 0, but I am running. I am going over on my x, so I'm running 1. So my rise over my run is 0 over 1, which is 0 divided by 1. So my slope is 0. A lot of people get confused when you have a 0 in the fraction on knowing if the slope is actually going to be 0 or if it is undefined. So I've got this little graphic here to help you remember this. This is how I help myself remember. When we've got the 0 on top of our fraction, so 0 over 1, you can turn that into okay. 0 over a number is okay, okay? 0 on top is okay. 0 on the bottom, though, that turns into no, okay? You cannot have the 0 on the bottom of a fraction. If you were to put this into the calculator, you put 0 divided by 1, you would get 0 on your calculator. If you put this one, no, right, into our calculator, 1 divided by 0, you would get an error code. It would say error. That would tell you that it's not okay. It's no. You can't do that. You can't have 0 in the denominator. You can't divide a number by 0, but you can divide 0 by numbers, okay? So error code, again, no. So we then would call that slope an undefined slope. So here, find the slope. We're going to count our rise over our run. So from this point to this point, I'm rising 1 and I'm running 1, 2, 3, 4, 5. Rise over run is 1 over 5. And you'll see that I'm going up the hill, right? So it would be puff, puff, positive. So it would be positive 1/5. Okay, our next one here. This time I'm going down the hill, so I'm going to be nice negative. So my slope is going to be negative. And I'm going to count my rise over run. Remember, it doesn't matter if I'm rising up or if I'm rising down. Okay, that's the rise is your vertical change, up or down. So here I'm going 1, 2 on my rise, and I'm running 1, 2, 3, 4, 5. So my rise over run would be 2 over 5. And again, this is downhill, so it's negative. So negative 2 over 5 is the rise over run. I went down for my rise. And so my slope would be negative 2 over 5. Negative 2/5. Okay, so remember the roller coaster here. The slope is undefined here when you have a vertical line, right? You're dropping off the cliff. It's undefined. So I am going to rise from this point to this point. I'm rising 1, 2. So my rise would be 2, but I'm running nothing. I'm not running anywhere. I'm not going anywhere horizontally on the Y. So rise over run, 2 over 0. Okay. Now, if you remember right, when we did this before, I showed you that if the 0 is in the top, it's okay. You can make it okay. But if the 0 is in the denominator, it's no. It's no. So you can't do that. You can't divide a number by 0. So you would get an error code in the calculator, and that means it's an undefined slope. Okay? A number over 0 is no. 0 cannot be in the denominator, undefined. So finding the slope using points. Here we're looking at the slope formula. Our slope M is rise over run equals our change in Y over our change in X. So Y2 minus Y1 over X2 minus X1, where 2 points on the line are X1, Y1, X2, Y2, right? So these are 2 ordered pairs, right? And we take our Y from the second ordered pair and we subtract the Y from this first ordered pair. We take the second pair and we subtract the X from the first ordered pair. So you do need to make sure that your the place in your ordered pair matches up on your fraction. So if you're taking the Y from here first, you got to take the X from here first, okay? And subtract those X values. So here we've got 2 ordered pairs. So I've already showed you how to determine slope off of a graph. You count your rise over run. When you're not given a graph and you're given 2 points, okay, Then you're going to use that slope formula, and you're going to take the y2 minus y1 over x2 minus x1. So in this case, we're going to take 5 minus 3 over 5 minus 1. Okay, subtracting our x's, our y's, subtracting our x's. Making sure that you take from the same ordered pair in the same position on our fraction. So 5 minus 3 is 2, 5 minus 1 is 4. So our reduced slope here would be 1/2, 1 over 2. So the slope for these two ordered pairs would be 1/2, 1 over 2. Okay, so here again, we take our y2 minus our y1. So we're going to take -4 minus -3. We have to keep these negative signs with it, okay? But remember, it's a subtraction problem. So don't forget about this minus the subtraction in it. So it's -4 minus -3. You can't just get rid of that minus because this is a negative number. You got to keep those signs with them, okay? So we would have to do keep, change to solve that. Over here, then we've got 5 minus 2, right? So here, -4 minus -3, we do keep, change, which would be -4 plus +3. Here, 5 minus 2. So up here, -4 plus +3 would leave me with -1. And 5 minus 2 would leave me with 3. So -1/3. -1/3. Okay, so 8 minus 1 and 4 minus -6. Here again, we're going to have to do keep, change. Remember, you have to keep that sign with it. It's still a subtraction problem, and we've got that negative sign with it. So we're going to do keep, change. We've got 8 minus 1, and we've got 4 plus +6. 4 plus 6. So we get 8 minus 1 is 7, and we get 4 plus 6 is 10. So we get 7/10. The slope of these 2 points, this line that goes through these 2 points, would be 7/10. Now we're going to find the slope using points. Okay, so here we've got kind of a word problem, right? We've got the cost of lunch is $22 for 2 people and $44 for 4 people. State the independent and dependent variables and the rate of change. And then we'll decide, is it a slope, right? So we've got here 22 for 2 people. Okay, so the cost of lunch is dependent on the number of people. As we invite more people to our lunch, our cost is going to go up. The number of people causes the cost to change. So the number of people is our independent, and the cost is the dependent. So cost of lunch over number of people. So we've got 22 minus 44, and then we've got 2 minus 4. Okay, so the 22 goes with the 2, so we got to put those in the same position in our fraction. And the 44 goes with the 4, so we got to put those in the same position in our fraction. When we subtract them, we get -22 over -2. Negatives cancel out, right? And we're left with 22 over 2, which reduces down to be 11. So the rate of change is $11 for each person, or $11 per person. So each time you invite another person to lunch, you're going to pay an extra $11. So do the points lie on the same line? Explain your answer. So we've got 3 different points here, and we're going to determine if they have a constant rate of change. If they all have a constant rate of change, we get the same rate of change, then we can say that they lie on the same line because they have the same rate of change, which would be its slope then. So we're going to take point G and point H, and we're going to subtract out our y's on top and our x's on the bottom, and we get -8 over 4, which is 2. Then we're going to take our, we can take our point X and our point H and subtract those 2, and we get this 16 over 8, which reduces down to be 2. And then we can take our point X and our point G, I think, yes. and subtract our y's here, 14 minus 6, and then that would be over 7 minus 3, and we get 8 over 4, which simplified reduced down is 2. So they are a constant rate of change. The rate of change is the same for each one of these, right? So it's our slope. The slopes are equal, so they are on the same line. Remember, if we get the same rate of change, constant rate of change, then that is a straight line, and that is also then our slope. And that is all I have on this. If there are any questions,